You know exactly when it happens. You reach for the shirt and the one still folded on the chair or tucked into the back of the drawer because you could not bring yourself to wash it. And you press your face into it and you wait. And then one morning, the smell is gone. The shirt is still there. The fibres are still there. Everything that once carried that scent is still there. But the smell is gone. This is not gradual. It does not fade the way colour fades from a photograph over years. It stops. And in its absence, there is a particular kind of devastation that no other loss in grief quite replicates. Because the smell was not just a memory, it was the closest thing to their actual physical presence that remained in the world, and then it was not. This has a mechanism, and the mechanism explains something that the absence by itself cannot. The olfactory system is the oldest sensory system in the vertebrate brain. Not old in the way neuroscientists sometimes mean when they use that phrase, as shorthand for evolutionarily conserved. Old in a more fundamental sense. Before there was a neocortex, before there was language or spatial reasoning, or the capacity to imagine tomorrow, there was olfaction. The earliest nervous systems appeared 300 million years before the first mammals. Essentially olfactory processing organs, with a rudimentary movement apparatus attached. Every cortical feature that followed was built on top of them, and the original architecture is still preserved, intact, inside your skull right now. Every other sense routes its signals through the thalamus before they reach the cortex. The thalamus is the brain's central relay station. Every signal from vision, hearing, touch, and taste passes through it, gets sorted and filtered, and then travels to the appropriate cortical region for conscious processing. Smell does not. The olfactory nerve projects directly from the receptor cells inside the nasal cavity to the olfactory bulb, and from the olfactory bulb, without relay, without thalamic checkpoint, directly into the amygdala and the hippocampus. The two structures most responsible for emotional memory and autobiographical encoding. This is why the smell of a particular soap can reconstruct a Tuesday afternoon from 30 years ago with more fidelity than any photograph you own. The pathway is shorter, the signal arrives faster, and it arrives in a region of the brain that does not distinguish the past from the present. That does not sort a person who is in the next room from a person whose existence has ended. The amygdala responds to the signal. The hippocampus attempts to complete the pattern, and for a moment the person is there. Dr. J. Gottfried at the University of Pennsylvania has spent decades mapping what he calls olfactory-evoked autobiographical memory, the process by which smell associations become encoded with a specificity and emotional weight that other sensory memories rarely achieve. His laboratory's work, published in Nature Neuroscience and the Journal of Neuroscience across multiple studies, demonstrates that smell memories do not degrade the way visual memories do over time. The neural representation of a smell, the pattern of synaptic connections stored in the piriform cortex, the brain's primary olfactory processing region, remains structurally intact for years, sometimes decades. The smell does not disappear from your brain. The representation persists. What disappears is the capacity to access it without an external trigger strong enough to activate it. Understanding the distance between those two things changes what the absence means entirely. Here is what happens in the nervous system in the days immediately after someone dies. Cortisol production rises sharply. This is measured data. Dr. Mary Frances O'Connor at the University of Arizona, whose laboratory has produced some of the most rigorously controlled physiological studies of acute bereavement in the scientific literature, has documented the cortisol profiles of bereaved individuals against matched, non-bereaved controls. The elevation is consistent, sustained, and statistically significant across weeks of monitoring. The hypothalamic pituitary adrenal axis, the system governing the body's hormonal stress response, shifts into a state of chronic low-grade activation that does not resolve in days, and for many people, persists for months. That sustained state has direct, measurable consequences for the sensory system most responsible for the smell. The olfactory epithelium, the thin sheet of specialized tissue lining the upper nasal cavity where olfactory receptor neurons live, is among the most cortisol-sensitive structures in the adult nervous system. Olfactory receptor neurons are biologically unusual in one critical respect. They are among the only neurons in the human nervous system that regenerate continuously throughout adult life. They turn over every 30 to 60 days under normal physiological conditions. Under chronic cortisol elevation, this regeneration slows. The turnover cycle extends. Receptor density drops below its normal threshold. The detection floor rises, meaning you require a stronger molecular signal to register the same smell at the same intensity. The grief state itself, through its hormonal architecture, has already begun to degrade the sensory machinery responsible for detecting the smell you are trying to preserve. If the science of what is happening in your body and in your nervous system during grief is something you want to understand more completely, the research behind this channel is gathered in the companion guide called What Feynman Knew About Grief. No wellness language, no comfort that has not earned its place in the peer-reviewed data. The link is pinned in the first comment below, and it is only available while this video is running. And before we continue, hold one question. When was the first time you noticed that the smell had changed? Not disappeared, but changed slightly off. Not quite right. Hold that moment, because the answer to that question is going to mean something specific. There is a second mechanism. It is more counterintuitive than the first. Olfactory adaptation is one of the most robust phenomena in sensory neuroscience. When you are exposed to a smell continuously, or repeatedly over a short period, the olfactory receptor neurons tuned to that particular molecular combination begin to downregulate. They retract from the surface of the epithelial membrane. The electrical signals they send upstream to the olfactory bulb weaken. Within minutes of sustained exposure, you can lose the capacity to detect an odour that was sharp and distinct 30 seconds before. The nervous system reclassifies the signal as ambient, background, and removes it from conscious awareness. In the weeks following a death, many people do what feels both necessary and impossible to stop. They smell the person's belongings, the pillow, the jacket, the unwashed nightshirt, the bottle of cologne still on the bathroom shelf since the last morning they were there. Each exposure brings the molecular signature of that person, the specific mix of skin oils, sweat metabolites, the particular bacterial flora that colonizes every human skin surface uniquely, into contact with the olfactory receptor neurons that were built to encode it. And each exposure triggers adaptation in exactly those receptor neurons. They downregulate a little more with each contact. The signal weakens, the smell fades. Not because the molecules have left the fabric, but because the sensory system responsible for decoding them has become selectively blind to that specific molecular combination. This is the paradox at the center of this mechanism. The act of trying to preserve the smell, the pressing of the shirt to the face, the opening of the cologne bottle one more time, the reaching for the pillow in the dark, is the precise act that accelerates its disappearance. The nervous system cannot distinguish a preserving gesture from an ordinary act of exposure. It responds only to signal frequency. Repeated signal. Decreasing response. There is no biological exception built into the olfactory system for grief. The mechanism operates the same way regardless of what the signal means to the person receiving it. Dr. Pamela Dalton at the Monell Chemical Senses Center in Philadelphia has documented what she terms olfactory emotional co-extinction, the parallel decline of both the perceptibility of a smell and the emotional activation it triggers, occurring simultaneously in bereaved individuals without corresponding molecular change in the source objects. The emotional charge and the detection sensitivity diminish together because they were built together. The smell was not a molecular event in isolation. It was a circuit, a network of connections linking the olfactory bulb to the piriform cortex, to the amygdala, to the hippocampus, that fired together because the person was present over and over for years, until the circuit and the person were inseparable in the architecture of the nervous system. Without the person, the circuit fires less often, and circuits that go unused begin to quiet. There is a third mechanism, and it operates in the molecules themselves. A person's scent is not a single compound. It is a volatile mixture, dozens, sometimes hundreds, of different molecules, each with its own evaporation rate, its own chemical weight, its own half-life in the physical world, sebum secretions from the skin, metabolic byproducts released through the pores. The specific strains of Staphylococcus epidermidis and Corynebacterium colonizing the skin surface, producing volatile organic compounds unique to that person, the absorbed residue of laundry detergent interacting with the chemistry of their skin. These molecules do not leave the fabric at the same rate. The lightest volatile compounds, those with the lowest molecular weight, leave first, within days in many cases. The heavier, longer chain molecules persist for weeks or months. What you smell in the third week is not what you smelled in the first hour. It is chemically incomplete, a subset of the original signature, with the most distinctive, lighter elements already dispersed into the surrounding air. And this matters neurologically because the olfactory bulb does not process isolated molecules. It processes patterns. Pattern completion is the core computational operation. The bulb receives a molecular input and attempts to reconstruct the full pattern it was trained on across years of repeated exposure. When the input is not merely partial but chemically altered, when the ratio of molecules has shifted because the light volatiles have gone, the reconstruction fails in a specific and identifiable way. The hippocampus receives an ambiguous signal. It attempts to match what arrives to the stored representation it holds of that person. The match fails. The person does not arrive through the reconstruction. Something adjacent arrives, something that does not quite resolve into them, that is almost them but not quite, and then it fades. The first time you noticed the smell had changed. Not disappeared, but changed not quite right. That was already the molecular signature, losing its internal coherence. The light volatiles leaving first, the pattern arriving at the olfactory bulb in a chemically incomplete form. Not quite right is the precise phenomenological description of partial pattern completion failure. The signal was there, the match was not. The research behind this video is gathered in the companion guide, What Feynman Knew About Grief, linked in the first comment below, still available while this video runs. And then there is the experience that almost no one expects. Weeks after the smell has gone, or months in a grocery store or on a crowded bus, or walking through a building that has nothing to do with the person you lost. The smell comes back for a fraction of a second. Not a version of it. Not something similar. The exact smell. The full molecular signature of that precise person. Your body responds before your conscious mind has registered what is happening. And then it is gone. Not faded. Gone the way it always goes. But for that fraction of a second, in an ordinary corridor, it was them. This is not imagination. It has a mechanism. The piriform cortex stores olfactory representations through what researchers describe using the language of attractor dynamics, a framework borrowed from physics that characterizes systems with stable internal states to which they return when perturbed. The representation of a specific person's smell encoded in the synaptic weights of the piriform cortex across years of continuous exposure exists as a stable attractor state in the neural network, even when the input pathway has been weakened by cortisol-driven receptor loss and olfactory adaptation, even when the external molecular signature has fragmented beyond reliable pattern completion, the stored attractor state does not disappear. It persists in the physical structure of the cortex, and when a partial signal appears in the environment, a stranger using the same shampoo, a room with a similar chemical profile, the olfactory bulb receives just enough input to perturb the piriform cortex toward that stable state. The full pattern activates, not because the smell is fully present, because the neural architecture that holds the pattern was never dismantled. Dr. Howard Eichenbaum at Boston University, before his death in 2017, spent decades studying what he called pattern separation and pattern completion. The hippocampus's dual capacity to distinguish between similar experiences and to reconstruct a full experience from a minimal cue. His research demonstrated that the hippocampus does not store recordings. It stores reconstruction templates. It uses whatever partial input arrives to assemble the full experience with as much fidelity as the available signal permits. When the signal vanishes, the reconstruction collapses. The person appears for a fraction of a second and then disappears again. Not because the memory of them is unstable, but because the reconstruction cannot sustain itself without continuous input. This is why smell leaves before everything else. Not because it is the most fragile of the senses. In neural terms, olfactory memory is among the most robustly encoded modalities in the brain. The direct amygdala pathway, the piriform cortex attractor structure, The hippocampal reconstruction template are all architectural features built for durability. Smell leaves first not because the brain holds it loosely. It leaves first because the external input that activates the stored representation is the most physically volatile element in the entire system. The molecules evaporate. The objects that carried the smell adapt the receptor cells that were built to decode it. And the living source, the only system capable of continuously regenerating the full molecular signature in its complete complexity, freshly, day after day, is gone. Research from the University of California, Davis, examining long-term olfactory memory retention in older adults, found that smell memories encoded with high emotional content showed significantly less neural degradation over decades than neutral olfactory memories or visual memories of comparable emotional weight. The amygdala's direct involvement in the original encoding appears to confer structural protection to the cortical representation. What degrades is not the representation. What degrades is access to it. What disappears is not the stored pattern. What disappears is the external key that was capable of unlocking it. If you want to hold onto this framework beyond the length of this video, the full neuroscience, the physics, the complete structure of what the data actually confirms about what persists in the nervous system after loss. The companion guide, What Feynman Knew About Grief, is in the pinned comment below, only available while this video is running. The smell left because the molecules evaporated and the receptors adapted and the signature fragmented and the pattern completion failed. These are documented measurable events in molecular biology and sensory neuroscience. They explain what happened to the shirt in the drawer, to the pillow, to the cologne bottle on the shelf. They explain why the smell left before the photographs faded, before the voice stopped playing on your phone, before any of the other things you expected to lose first. The molecules are too light, too volatile, too dependent on a living system to replenish them. But the neural representation, the pattern the olfactory system built over years of continuous exposure, has not undergone the same degradation. It is held in the synaptic weights of the piriform cortex, in the attractor dynamics of the olfactory limbic network, in the hippocampal reconstruction template that still knows exactly how to assemble the full pattern from the smallest available input. It fires for a fraction of a second in a grocery store. It fires before language reaches it. Along a pathway that bypasses conscious processing, because the route from olfactory bulb to amygdala is shorter and faster than the route from sensation to thought. The shirt is in the drawer. The molecules have dispersed into the air of the room. And somewhere in the piriform cortex, in a stable attractor state that has not degraded, that has not been washed or evaporated or adapted away, the full pattern is still there, waiting for a signal strong enough to unlock it. And occasionally, in the least expected place, finding one